Working?
Oh, it's back. Yay. So, lots of people have given really good talks about the things that they've been doing and the technical details of the problem and the solution. But right now, I think most of us are quite tired and my head hurts. I don't know about yours. So I want to end with something a little higher level and talk about sort of work in progress, like what we're doing at the moment and what we're working towards. Specifically, we're interested in system software, kernels, specifically hypervisors. And really, we want to think about reasoning about these software with respect to our weak memory models. Due to the nature of the talk, I'm going to be talking about a lot of things that are sort of currently in progress with a bunch of collaborations with people. And so it might change over time, but we'll see. So as some of you will know, Peter has embarked Cambridge upon this grand verification adventure of a hypervisor. And the exact details of how this proof will go are not so important. Peter's going to give a keynote at Prisk on Saturday, where he's going to talk about some of the challenges associated with that. But for this talk here, we can think of it as a kind of motivating example for the kinds of weak memory things that we see in real system software. And we're going to use this to motivate the kind of architecture or semantics that we need in order to do that kind of reasoning, specifically for ARM in this case, although you could do it for many other architectures. And then we want to know how we can build reasoning tools above this, above, this complicated system semantics that we're building, that will allow people to reason about their code in a variety of ways. And Thibaut already mentioned that there's going to be a talk on Thursday by Zhongwon and Angus talking about their program logic to do that. So let me tell you a little bit about this hypervisor. I'm not going to go into too much detail, but essentially it is a production hypervisor in that if you have a fancy Pixel phone, you're probably already running it, being entirely developed by Google. So we're not involved in the development at all. We're aiming to verify the code that they write in the way that they write code. And I'm going to hand wave exactly what we're going to verify. Again, it doesn't really matter so much for this talk. So what kind of semantics do we need, and what kind of semantics do we have already? And what do we need to add on top of that? So ARM is complicated. It's very big, and there are lots of things that really any hypervisor or any system software needs. Now, I'm going to go into detail in a second, but I want you to see that on the left here we have a bunch of features, or really they're language fragments from ARM. And on the right we have a selection of models. Now this is a selection of models and a selection of features, not a complete set of either. But I want you to see that we have some models have some of the things, some models have some of the other things, some are work in progress, but we don't even have all of the things in all of the columns. Right? There are some rows that are completely empty where we just don't know about them. Some of them appear in both. It's kind of a mess at the moment. So that's unfortunate because what we really want is one model that we can use. At the moment, we don't have that. So what are these features that we need? So if you think about any system software, any kernel, microkernel, any hypervisor, it's trying to compartmentalize multiple smaller chunks of execution of processes or operating systems beneath it. And to do that, it's going to interact with the hardware's instruction fetching mechanism and its required cache maintenance. And we have multiple models for that now, like my original one and updates by ARM. And also, these systems care about security, and the way that they enforce security properties, mostly via isolating these different processes and operating systems, is through hardware virtual memory. And hardware virtual memory is a complicated topic with many people working on it at the moment. And there's a bunch of different things that you need, that really anyone would need if you do this. Some done by me and Cambridge, some extended by ARM, some overlap. But there's a problem in that you need both of these things, and we don't have a model that has both of them and the interaction between them. So we're currently missing like a key part of that. And then on top of this, you have other things that you need. So the way hardware deals with changing privilege levels is with exceptions and interrupts. And we currently don't have, I believe, any model that describes the relaxed behavior of these exceptions. And this is some work in progress with Ohad Kamar in Cambridge, although I don't see him in the room at the moment. And also, any system software is going to have to touch system registers in ARM. This is how you interact with the hardware directly. And these themselves have their own relaxed behaviors that turn out to be much more complicated than we started with. Now, lots of other people have shown litmus tests. If I start showing litmus tests where half of the instructions are cache maintenance instructions, people scream. So I'm not going to show any of those tests. But you can imagine that there's a lot of complexity still needing to be done in order to even have all the parts. And then when you start putting them together, you get the interactions between them. And then we don't have those interactions either, and currently it's all fragmented. So that's unfortunate, but it's kind of understandable how we got into this situation, right? Many people have worked on sort of ARM models, many people in this room, and what you do is you start with a model and you want to add some extension, some language fragment, or some behavior to it. And so you add your thing, and it then slowly diverges from everyone else. And so you end up with all of these little models made by many different people. And yes, I'm like responsible for half of the divergence at this point, but that's how it goes. So we have this problem, like how do we move towards having a single model with all of these interactions all combined together? And the answer is, unfortunately, I don't know. It's a lot of work to do, and nobody is really pressing to do it at the moment, except maybe ARM. But it's something that we absolutely need if we want to verify real systems code with respect to what the hardware is actually going to do. So this is not a good start to our verification story. One thing I did want to say is that this image reminded, when I was rendering this slide, I had a reminder of this old image that many of you have seen from program objects, where you have all of these different artifacts that are all connected in some way, and there are lots of them. But there's a key difference here, and I think Matt pointed this out a long time ago, that each of these this isn't a bad state, right? All of these program objects, they have a good reason to exist as sort of independent, separate entities from all the others. But that's not really so obviously true here. These are all trying to model the same language underneath, the same architecture, and they exist separately because of convenience and just happens of history, rather than having themselves each an excuse to exist separately. So that's kind of interesting, and I think that means that we're in a kind of worse state because of it. But one thing I do want to say is that so I think right now downstairs ARM are having this workshop where they're discussing their tooling, and ARM recently have done a lot of work in sort of bringing these things together and trying to build a single model. And our hope is that in the next few years, ARM will produce a single model for all of the behaviors that we need, in collaboration with all the other people on that slide, of course. And then we'll be able to use things like what Tibo was talking about to create the formal models on top of it. So whilst the situation today looks quite dire, to have all of these things even in place, we are moving in the right direction. And I think that's what's going to make this possible. So assuming we have that, how are we going to reason about software? Well, we're going to make program objects, of course. But also we can do sort of refinement arguments, such as with Gil's conditional contextual refinement framework, and model checking and other methods. But I want to lay out, in principle, 2 ways that I think we might do this. So one is that we can reason about code directly in the semantics of the language, with all of that complexity. And I'll talk briefly about this later. But the thing I really want to talk about is this idea of reasoning about the code by abstracting away the language first. We don't want to talk, in most of the time, we don't want to talk at all of that complexity in ARM, because there's just, especially when you add all these system features, far too much of it. So how do we do that? Well, there's this thing that you can notice about all of these models, and that is if you have a data race, so if you think about your traditional user mode, data-only, nice memory models, you have data races between reads and writes, but if you don't have any of these in your program, then your semantics sort of collapses down to this nicer model that you can use, this SCDRF property. And as you work your way into the systems world, and you add all of these extra instructions. I mean, you get fancy things like instruction cache cleans and TOB maintenance and random barriers, but really you're still just looking at weird data races, right? You still have, a read and a funky kind of read, a write and a funky kind of read, and there may or may not be some of these magic instructions, but if you squint, it just looks like a data race. So if you write code in the way that the architecture tells you that you should, in order to avoid all of that complexity in the model and the complexity in your head, then what you're doing, if you squint, is eliminating these data races in your program. And if you do that, then what it should be is that your program's behavior should collapse down to a simpler model. So all you have to do is pick the right kind of data race, and then you're able to build a simple race-free model, which you can show to be a sound abstraction of the architecture. Or this is our plan, to show that it's a sound abstraction of the architecture. And then you can use this simple race-free model and compose it with your program. In this case, we're talking about whole machine models. Your program is just an initial state of your whole machine. And then you're able to verify that that whole machine plus this state satisfies some specification that you have. And then if you do that, you get, hopefully, that your program, with respect to the real machine, was sound for that, or implements that specification for free. And this is not a novel solution. We all know about this kind of technique, but it's incredibly compelling when we're dealing with these more and more complicated memory models as we add more and more features, especially as we work into the world of systems, where the architects tend to have more of an attitude of do this or die. So one thing I want to say is this is probably how we expect most reasoning of most code will go. Right? Most code follows that pattern that the architects say. They say do this, and people do it, and then you don't have to worry about it. But what about programs that do exhibit these races? They really do exist. Specifically, you'll find them in like core synchronization primitives, or in that flush write barrier that Matt was showing us. These kind of things can exhibit those races, but very rarely. And in those cases, you really can't do this trick of abstracting away the language. You really do have to reason directly in the language, in the original language semantics. And this is the work by Angus and Songwon in their Axel program object, which is directly over that axiomatic semantics. But we really hope that you don't have to do this kind of reasoning too much. So, because of the nature of the talk, we haven't actually gone through and done all of this yet. It's more of a plan, and so I don't have a conclusion. Maybe come back in a year and I'll tell you how it went. So that's kind of the end.
Thank you. That was a great talk. A few questions.
So I think one of the things that you can suffer from when you do big formalizations is instead of having many small, somewhat consistent things, you have one big, deadly mega thing which can never be changed ever in the future. So if you're going to build this sort of mega model which has every single switch turned on, how do you maintain it over time? Because it feels like a lot of the reason that this complexity, you have these different variants, is it's quite convenient to have one kind of abstraction for one thing, another abstraction for another thing. Have you thought about that kind of formal model maintenance kind of problem if you're building this giant model?
So it sounds painful to have the big model, but I don't see a way. I mean, you have to have the big model to do the verification if you want to do the verification over the real architecture, because these features, it's not like here's a collection of 1 million features, let's just switch them all on. This was a collection of 10 features that you really must have, because some of them have security implications if you get that part of the kernel wrong. Some of them are sort of core parts of how the kernel works. Yes, there are also 1 million features on top of that you can switch on and off, but even just the core part of the semantics we don't have, at least not all in one place, and even that is overwhelming. Now, I don't even want to think what happens when you add all of the ARM extensions and the, I don't know how 500, 600 instructions it has. And so yeah, when you extend it out to all of that stuff, maybe it becomes unmaintainable, but at least for this core, I don't think we have a choice.
Here. I like a lot this analogy that you have between data rate freedom and the system models. However, what is not clear for me is if those system models already have these similar properties, or this is something that you claiming that we should aim for?
So in a sense, it's kind of a goal of the architecture. The idea that, if you have a race between one of these weird reads, because they're like instruction fetches or translation table walks, and a write to it, then if you do what the architecture says, you shouldn't get any weak behaviors from it. That's sort of one of the goals of the architecture is for these things where you have explicit maintenance of caches, for example, is that you're recovering coherence. You're sort of recovering back to that state. And if you can't do that, then one would argue that the architecture has a problem. And so far, at least, so it's kind of interesting. It's like there's not one definition of race here. And the analogy does break down a little bit. You have a sort of choice of that abstraction. Normally, when you do like program objects, your abstraction is you get to choose your heap and your resources. Here, the abstraction is you choose what that race looks like. And it's not that your weak memory behaviors will entirely go away with all of those choices. You get to choose like this, and those behaviors go away, or choose like that. Really, you're choosing a programmer discipline, like how the program is written. That if you always, you have these barriers in these places, whenever you write to one of these variables, you do this way, then you can eliminate a bunch of behaviors. Sort of like if you're familiar with triangular race freedom, if you don't have this shape, then you don't get this behavior, but you still get this stuff.
I think this might have to be the last question. Or do you want one? Okay, wait. Let's go for it first.
I know there's a lot of tools in this suite of yours. What's the performance like on large-ish programs these days?
So which tool are you talking about?
Isla?
Well, so Isla, the symbolic evaluation engine is very fast. Right, you can just give it stuff. The actual axiomatic model checking part of it has a huge problem when you introduce translation, specifically because if you think about what's happening for a translation is you're reading this page table. And if you have multiple stages, then for every single access, your trace contains like 24 other read accesses, and you get this massive explosion. And yeah, Isla doesn't cope with that very well. We have some optimizations, some are sound, some aren't so sound, that seems to improve it. But yeah, this is a big problem, and it's only going to get worse. Yes, of course.
So, like, there's general programming, concurrent programming, like there's fewer people do that generally and then this sort of systems level, right? There's a handful of people at a handful of companies that do it.
Yes.
So I wonder if, because it's such a small number of people, what is the right way to sort of go about it? Because you're not trying to do it for like arbitrary programmers, so like...
No, we're not trying to do it for like an arbitrary programmer. So why are we doing it? Well, there's a question of why are we doing it, right? I mean, we're doing it because we're academics and we enjoy proving things correct and we like a challenge.
Gluttons for punishment.
Exactly. But so why would they care? Well, the point of like a hypervisor, like the one that we were talking about here, is to be a security device. So if it goes wrong, then they have a huge problem. And so the cost benefit to them, or really I would hope to anyone, to do some of the work. You don't have to do full verification. So one of the things I was talking about here was like you can have a program logic and you do verification, but you don't have to go that far, right? You can have this abstract model and then do runtime checking against it. You can write separation logic style program logics, but then do runtime checking of them rather than trying to do a whole proof. And I think the PhD student chap behind you, Rinny, is part of that project. So you should talk to her. And this is this has a much better sort of cost-benefit ratio for them, but uses a lot of the same ideas. And so that's a way forward, especially the specifying part. I mean, in the end, you just tell them that they have to write specifications for some parts of the code and think about where some of the barriers and things have to go. And that's already like so much better, right? So you get diminishing returns as you go up the stack for sure.
Okay, great, thank you. Well, on that note, we might conclude the session, and that also concludes the workshop. First, let's thank Brent.
Yeah, thank you very much.
So yeah, thank you again for contributing, and yeah, it's been a great day. Enjoy the rest of your week.